So I'll be talking about data-driven distributionally robust optimization using the Wasserstein metric, and this is actually based on joint work with Peyman Mohajeri Isfahani and with Soroush Afiyazadeh Abadeh. I hope I pronounced these names more or less correctly. Okay, so what I would like to do in this talk is I would like to study single-stage stochastic programming problems. So here the goal is to minimize the expected value of some loss function. So this loss function is denoted by L. It depends on the here and now decision X, which needs to be chosen from a feasible set script X. And now the loss function also depends on a vector Xi of random variables. So in stochastic programming, we assume that we know the distribution P that governs this random vector. And so what we would like to minimize is the expected value of this loss function. Okay, so what we need to remember here is that P is the distribution of Xi, and yeah, it's a simple single-stage stochastic optimization problem that we would like to solve. Now, this is it's the most simple stochastic optimization problem you can think of, yet it has already quite a number of important applications. So first of all, actually the famous news vendor problem, which is the most basic model in supply chain management, is exactly of that form. So here you minimize overall ordering decisions, the expected news vendor cost. This single-stage stochastic program also shows up in finance, specifically in portfolio optimization, where you minimize overall possible portfolio allocation vectors, the expected value of some, say, disutility function. However, this stochastic program also shows up in machine learning, specifically in regression and classification problems. So if you would like to train a support vector machine, or if you'd like to solve a simple regression model, then you can also formulate it as a single-stage stochastic program of this form. Now, okay, so I hope I've convinced you that this is a simple yet already quite general class of problems. However, I would like to argue now that in spite of its simplicity, this class of problems suffers from two fundamental shortcomings. So very severe problems. So the first of one is that this problem is very hard to solve, even in very simple settings. And I would like to show this to you with an example. So this is a simple production problem. Assume that X is a vector of production quantities for different goods, and Xi is a vector of unit production costs. Okay, so and these are uncertain. That means that the inner product, X transpose Xi, is the total production cost. Now, in our simple stochastic optimization problem, we try to find a vector X of production quantities that minimizes a risk measure, in particular that minimizes the so-called first upper partial moment. So the first upper partial moment just evaluates the expected value of the cost X transpose Xi above a certain threshold B. Okay? Now, it turns out that even in the simplest setting, when the unit production costs, so when the different components of the vector Xi are mutually independent and uniformly distributed on 0, 1, so and on the interval between 0 and 1, so it's really the simplest possible stochastic model you could assume for the random vector Xi. So in this case, it is already sharply hard to evaluate the objective function or to evaluate the risk of a particular production plan. Okay? So that means that every known algorithm that we could use to evaluate the risk of a fixed X would have a runtime that grows exponentially in the dimension of the problem. So that would be in the dimension of the vectors X and Xi, the number of products. And this is just about evaluating the objective function for a fixed decision X. This is not even about optimizing the objective function. So this is the so-called curse of dimensionality. It states that, yeah, if the dimension of a stochastic optimization problem grows, then it becomes increasingly or exponentially hard to actually solve the problem. And this curse of dimensionality really seriously affects the problem sizes, or the problem sizes that we can actually address in practice. It seriously limits those. Okay? So that's the first fundamental shortcoming. There is a second fundamental shortcoming, which is called the optimizer's curse. And I would like to argue that this shortcoming is even more fundamental. So it turns out that the probability distribution P of the random vector xi, in most applications that come to my mind, is actually unknown. And so therefore it has to be estimated either by using historical data, using tools from statistics, or it has to be estimated from expert advice. And in any case, it will be affected by estimation errors. So that means that the fundamental input for our stochastic optimization problem is fundamentally unknown to us. And actually it turns out that any estimation errors in this distribution, so in the input of the problem, they are inherited by the output of the problem, that is the optimization results. And so this is very detrimental, and actually, of course, this is just a manifestation of the notorious garbage in, garbage out phenomenon, right? So if the input of your problem is incorrect, then you should not expect the output to be correct. So I would like to motivate this or explain to you this optimizer's curse with a simple example. So assume that you're a manager of a company, and there are 10 different projects from which you can choose 5 to implement. So it's basically, you have budget for implementing, realizing 5 of these 10 projects, and you need to decide which ones. Now, the net present values, or the expected net present values of these different projects, are visualized by the blue bars here. So which 5 projects should you choose? Well, it seems that this is like a very simple question. Of course, you would just choose the 5 projects that have the highest expected net present values. By choosing those, you will essentially maximize the average net present value across those projects that you have selected. Okay? Now, in reality, the net present values of these projects are unfortunately not known to you, because these are expectations. So they depend on the uncertainty, they depend on the probability distribution of any random variables that may affect these projects, like future demands, future prices. And therefore, all of these net present values are affected by estimation errors, which you can visualize here by these error bars. Now, just for the sake of argument, let's make a very simple assumption. Let's assume that we have estimated the net present values, and that actually the net present values of half of the projects have been overestimated, shown by green bars, and the other half have been underestimated, shown by orange bars. So that means that the estimation errors actually cancel out on average across all the 10 different projects. And this is quite a natural assumption if you have a large number of projects. Okay, so now assume you're the manager. You need to choose the 5 projects that you would like to implement. You do not see the real expected net present values, but you only see the estimates here. So a manager who only sees the estimates will order the projects like this, and will actually then choose the 5 projects that have the highest expected net present values, or the highest estimated net present values. And now you see the fundamental problem. The fundamental problem is that projects whose net present values have been overestimated are much more likely to be chosen. So projects visualized in green here are much more likely to be chosen because they're overestimated. Those that have been underestimated, the red ones, are unlikely to be chosen. Actually, only one is chosen here. What this means is that the estimation errors do not cancel out across the 5 selected projects, but they are actually positive on average. And that means that the decision maker in this case actually overestimates the average net present value across the selected projects. So the decision maker is too optimistic about what will happen in reality. Now, what will happen in reality? This we can figure out by looking at the true net present values of the 5 selected projects, which look like that. And the average of the true net present values is visualized by the blue dashed line here. And of course, it is necessarily smaller than the theoretical maximum, visualized by the gray dashed line, which could have been achieved under perfect information. So what happens here is something that happens quite systematically. If you use estimates as an input for an optimization problem, you overestimate the profit you will make. So, or in this case, the net present value, you overestimate it. It's visualized by the red dashed line. What really happens, the profit you will really make in reality would be reflected by the blue dashed line. And this one is necessarily smaller, and in particular also smaller than the theoretical maximum you could have achieved under perfect information. So the difference between what you think you get, the red line, and what you actually get, the blue line, is sometimes called the post-decision disappointment. So what this tells us is that if the input estimates of a stochastic optimization problem are unbiased, so the errors, they cancel out on average, then nevertheless the optimization results are biased. And actually, they are biased in a bad way, so that you're too optimistic about what you can achieve, and you will be disappointed once you implement your decision and see what actually happens. So this is called sometimes the optimizer's curse, or so other people call it the optimization bias. That's a phenomenon, actually, that's also reminiscent of what is called overfitting in statistics. Okay, so let's take a step back and let's look more abstractly at the kind of problem we would actually like to solve. So as I said, in most applications that come to my mind, we do actually not know the probability distribution that governs the uncertain parameters. In many applications, however, we will have some statistical information about this distribution. So what I will assume throughout this talk is that actually we have access to n different training samples, here denoted in green by xi hat 1 up to xi hat n, which follow the unknown distribution p. Now, given this training data, that's the only thing I know about the distribution, right? Well, I would like now to develop a method of data-driven stochastic programming. So what I have to do is I have to find some method that transforms the training data, xi hat n to xi hat 1 to xi hat n, to some decision, a data-driven decision, x hat, and some performance certificate, which I denote by j hat. Okay, so at this point, what is in the black box is just an arbitrary transformation that maps the training data to a decision, which I assume is feasible and hopefully near optimal in the true problem, and the performance certificate. Okay. So that's very abstractly spoken. Now assume that we have such a method, and let's assume we have found a data-driven decision x hat. How do we assess how good this decision actually is? Well, like in machine learning, the best thing we can do is we can basically simulate our loss in this case by using actually a different set of data, namely a set of test samples, m different test samples, which are denoted with red letters, by xi hat 1 up to xi hat n. So also assume that they've come from the same distribution that we don't know, and they're independent. So if I simulate what happens with my decision, I will just evaluate essentially the sample average of the loss of my decision over these test samples. And now, if the number n of test samples tends to infinity, under mild conditions, the law of large numbers will tell us that this sample average actually converges to the expected loss of our data-driven decision x hat. Now, in this expected loss, the expectation is evaluated with respect to the distribution p of a single test sample xi, which is independent of the training samples. Okay? So actually, throughout this talk, any quantity that has a hat is a quantity that is accessible to us. It's a function of the training data. Okay, so the x hat here is, of course, a function of the n training samples. And therefore, the expected loss of x hat is a random quantity because it depends on our random draws of the training samples. Actually, this expected loss is often called the out-of-sample performance of the decision x hat. Okay, so that's just terminology. The out-of-sample performance, well, it's the objective function in our stochastic program of a feasible decision. We assume that x hat is feasible, and therefore this out-of-sample performance is necessarily larger or equal to j star, which is the optimal value of our true stochastic program, which we could solve if we knew the true distribution. Okay. Now this is of course a trivial inequality and is not very useful. What we're after here in this talk is something more useful, which we call a finite sample guarantee. So we want to use the training data not only to construct a near optimal decision x hat, but also a performance certificate j hat. And we would like that this performance certificate j hat exceeds the out-of-sample performance with a high probability 1 minus beta. Okay, so that's the expression at the bottom of the slide. Here, the probability is evaluated with respect to the distribution of the n independent training samples, which affect x hat and j hat, the green quantities. Okay? So a finite sample guarantee is a useful thing because it tells us something about how desirable our data-driven decision x hat is. Okay? So what we would want to achieve is that we find a number j hat, which is a small number. However, we're guaranteed that with high probability 1 minus beta, it exceeds the actual cost or expected loss of our decision x hat. Okay, so that's what we would like to achieve in data-driven stochastic programming. Now, of course, I need to tell you how we actually are going to achieve that. J hat should be an upper bound. So, okay, so I'm sure. Okay, my mouse is not visible, but anyway, so yeah, the j hat should be like an upper confidence bound on the out-of-sample performance. So the j hat is random because it depends on the training samples. So the training samples are randomly drawn from the distribution p to the power n, right? And the out-of-sample performance is also random because it depends on x hat, and x hat is randomly depends on the training samples, which are again randomly drawn from their distribution. So on both sides of the inequality, we have a random quantity. And what we would like to make sure is that, well, the j hat is an upper bound on the out-of-sample performance for the majority of training data sets I can sample. So for a fraction of 1 minus beta of all training data samples that I can generate, I would like this inequality to be satisfied. With probability beta, it's possible that I find a training data set for which the out-of-sample performance actually could be bigger than the j hat. I need to accept a small error, otherwise I will get a decision or I will get a method that will be too conservative. And I hope it will also be more clear because I will give you a first example now. So, okay, so what should we put in our black box? What should be the method of data-driven stochastic programming? Well, the simplest thing we could do would be to solve the so-called sample average approximation problem. So this sample average approximation problem solves an approximation of the true stochastic program constructed from the training samples. In fact, so since we do not know the true probability distribution of xi, we cannot minimize the expected loss. But instead of that, what we do here is we minimize the empirical average of the loss with respect to the training samples. Okay? And of course, this is a quantity we can evaluate because we do know the training samples. So if I solve this SAA problem, then because the objective function of this problem depends on the training samples, it is clear that its optimal solution, x hat, will also be a function of the training samples. And this sample average approximation method is really the simplest method to data-driven optimization, and it's very popular, mainly for two reasons. The first one is it's extremely simple. So you just minimize the average to sample average, and there's nothing complicated to be done. There are very powerful methods that have been developed to solve problems of this kind, like stochastic gradient descent methods and so on. So these scale to really high problem dimensions. And besides that, it turns actually out that the sample average approximation method enjoys a finite sample guarantee of the type I described on the previous slide. So in fact, one can prove that the optimal solution, x hat, of the SAA problem is an epsilon suboptimal decision for the true problem with high probability if the number of samples n is large enough. Okay, so we have a finite sample guarantee. That's the inequality with 1 minus beta on the right hand side here. If the sample size n is bigger than this quantity shown at the bottom right of the slide. So Shapiro and Demirovsky, they proved this bound. Now, this is a very nice result, okay, because it tells you exactly how many samples you need to get a good, high-quality solution. Now, however, there are some problems. So first of all, this bound depends on the diameter of the feasible set X, which means that this set needs to be bounded, otherwise the bound is meaningless. Also, this bound depends on the Lipschitz constant of the loss function L. So that's the Lipschitz. So what we require here is that the function L is Lipschitz constant in psi uniformly over all X. Okay, and that's also something that is not every problem would satisfy. So these are quite restrictive assumptions. Moreover, the required sample size scales as 1 over epsilon squared, where epsilon is the level of accuracy that you require, so the suboptimality level of your decision. And that means that, well, the number of samples that you need could really be very, very large. Now, this is no problem if you actually knew the true distribution and you could use a random number generator in your computer just to generate an arbitrarily high number of training samples. However, in reality, often, as we said, right, we do not know the true distribution, so we cannot generate additional samples easily by random number generation. Instead, our samples maybe are historical observations, and if we want more samples, it basically just means that we have to wait longer to see more observations over time series. So in practice, n, the number of training samples, is pretty much something that is given to you, and you have very little control over that. And that means, well, if the inequality at the bottom of this slide is violated, and this will often be the case, then you have no guarantee about the quality of the sample average approximation solution. So here's a particular example. Imagine that we would like to solve a mean risk portfolio selection problem. So this is a problem that tries to allocate capital into 10 different assets and tries to minimize a combination of the expected portfolio loss and the conditional value at risk of the portfolio loss. Here, rho can be seen as some sort of a risk aversion coefficient. Now, in order to have a controlled experiment, I make up a statistical model for the vector psi of asset returns. So the details are shown on this slide. Basically, it's a model where there is a systematic risk factor psi, and there are some idiosyncratic risk factors theta I that are specific for each asset, and I mean, they're all normally distributed, so that means the vector of asset return is somewhat normally distributed. All of this doesn't really matter that much. I just need to make up such a model so that in my experiments, I can generate an arbitrarily large number of samples to gain some insights. Okay, that's just to gain insights. In reality, I would not be able to do that because in reality, I do not know the true distribution. Now let's look at an investor who would like to solve this problem. And let's assume this investor has 30 training samples. So we have observed asset returns over 30 months in the past, and that's the only information I have about the portfolio, about the asset returns, say over the next month, over the distribution of returns of the next month. So I could solve a sample average approximation version of this problem using these 30 training samples. Now the results are shown on the right-hand side. So actually, I can generate these 30 training samples, say 10,000 times, and each time I can solve the SAA problem. And of course, because the samples are random, the solution of my SAA problem will be random. So the optimal value will then follow some distribution, and actually this is visualized by the green histogram on the left-hand side. Okay? Now, each time, for each set of 30 training samples, I can solve the SAA problem and get an optimal investment decision X hat. Now, this decision X hat depends on the samples. And now, because I know the stochastic model, I've made it up myself, I can generate a huge amount of test samples to evaluate the true mean risk objective of this decision X hat. Again, if I repeat this procedure, say 10,000 times, then I get 10,000 different answers because of the randomness of the training samples. And well, the out-of-sample performance, so this mean risk objective of the different data-driven decisions is visualized by the red histogram on the right-hand side. Now, if I generate a huge number of samples, I can also, with very high accuracy, solve the true problem, where essentially the true distribution is known, and the optimal value J star is visualized by the black dashed line on the right-hand side. So what you can see here is actually the optimizer's curves that we've seen before. So the in-sample results are too optimistic, right? And the sample average approximation underestimates the risk that can be of the optimal portfolio. So that's because the green histogram is on the left-hand side of the true optimal value. Of course, out of sample, I can never do better than the true optimal value. So the out of sample values, they are all strictly higher than the true minimum that could only be achieved if we knew the true distribution. And you can see the two distributions, the in-sample and out-of-sample distributions, they're quite separated. So there's quite a bit of discrepancy between what you think you get in green and what you actually get in red. Then, okay, so that means that the conclusion of this is that the sample average approximation is very simple. So it's popular. However, it doesn't work well if you don't have many samples. Like in the case of the 30 samples for the portfolio problem, this was clearly not enough because there was a huge discrepancy between in-sample performance, what you believe you will get, and out-of-sample performance, what you will actually get if you use that method. And, well, how could we improve the performance? The only way to improve it is to increase the number of samples. However, in reality, we cannot do that because the samples may be historical observations, and the only way to get more samples is just to wait longer, okay? And that we may not be able to do. We may have to make a decision today. So what I would like to propose here in this talk is actually, instead of the SAA problem, to solve a distributionally robust optimization problem, which is shown here on top of the slide. So here we basically use the training samples to construct a so-called ambiguity set, P hat n. Okay, so P hat n should be interpreted as a family of probability distributions. Actually, it should be interpreted as all the probability distributions that could have generated the training samples that I observe. Okay, and we'll later talk about how to construct this ambiguity set. Now, our decision problem is actually formulated as a zero-sum game, where the decision maker first chooses the decision X with the goal to minimize expected cost, and then some fictitious adversary, people often think of this as nature, chooses a distribution Q in the ambiguity set P hat with the goal to maximize the expected loss. So with the goal to hurt the decision maker as much as possible. And the idea is that if we solve such a distributionally robust optimization problem, the decision maker basically prepares for the worst that can happen, and by preparing for the worst, actually, often we do quite well in the average case, or in more likely cases. Okay, so if you optimize the performance in the worst case, then we actually will often do quite well in average cases. Okay. So here, this also gives us a method of data-driven optimization because, okay, I use my training samples to construct this ambiguity set and then I solve the distributional optimization problem. Now, my X hat is now the optimal solution of this problem, and clearly this is a data-driven decision because my ambiguity set and therefore the whole problem I try to solve depends on the training samples, and therefore, of course, the optimal decision also depends on the training samples. As the certificate J hat, I actually define it as the minimum of my distributional robust optimization problem. Okay, so of course, this is also a function of the training data. Okay, so that's my proposal. Now, of course, we need to decide how we construct the ambiguity set P hat n from the training data. And at the bottom of the slide, I would like to propose a wish list of desired properties that this ambiguity set should satisfy. So the first property is, I would like to design the ambiguity set such that the optimal value and the optimal decision of my distributional robust optimization problem satisfy a finite sample guarantee of the kind as we have discussed it before. Second, I would like to make sure that if the number of training samples tends to infinity, then in some sense, the optimal solution of my distributional robust optimization problem should converge to the true optimal solution of the problem based on the true distribution, which I cannot solve. And last but not least, I would like to construct an ambiguity set such that the distributional robust optimization problem can be solved very easily. And by this, I mean that it is in the same complexity class as the sample average approximation problem. So it should not be much harder to solve the SAA problem. If it was very hard, of course, then even if we have great statistical properties, the whole procedure would not be very useful in practice if you cannot compute the decision. Okay, so this is my wish list. So now I'm going to propose a way for constructing the ambiguity set. And okay, so what I will do here is first I construct the so-called empirical distribution on the training samples, which I denote by P hat n. Okay, so this is just the uniform distribution on the training samples. So that's a discrete distribution with n discretization points. The discretization points are the n different training samples. And each training sample gets a probability 1 over n. So it's the uniform distribution of training samples, okay? And now, as the ambiguity set, I define it basically as the family of all distributions Q that live on a given set, capital Xi. So this you should think of as the support set of the distribution. And, well, the distribution Q should have a distance of at most epsilon from the empirical distribution. Okay? So you should think of this ambiguity set as a ball in the space of distributions, where the center of the ball is the empirical distribution, and the radius of the ball is a parameter epsilon that I choose. The idea is that, okay, we know the empirical distribution is not the true distribution, but it is, well, the distribution that is actually used in the sample average approximation, right? The sample average approximation just replaces the true distribution with the empirical distribution in the objective function. So there is reason to believe that the true distribution should not be too far away from the empirical distribution. And the epsilon here is, well, the tolerance that we accept. Okay, so I will discuss this, but I first need to say I need to complete my this description of the ambiguity set. So it's a set of all distributions in a ball of radius epsilon that live on the set capital Xi. And what remains to be done, I need to tell you how I measure the difference between two different distributions. So what we propose here is to use the Wasserstein metric. Now, the Wasserstein distance between two distributions Q1 and Q2 is defined as the difference between the expected values of some test function f evaluated under Q1 and Q2. And then, well, then we need to maximize this difference over all possible test functions f that are Lipschitz continuous and have a Lipschitz constant smaller or equal to 1. Okay, so that's how this Wasserstein distance is defined. Okay, so yeah, so that's the proposal for the ambiguity set. And in the rest of the talk, what I would like to explain to you is that if we construct the ambiguity set in this way, then our distributional robust optimization problem satisfies all the three properties of our wish list. So first of all, it offers a finite sample guarantee. Second, it offers an asymptotic guarantee, so it gives decisions that are asymptotically consistent. And third, we will be able to see that the problem is in the same complexity class as the SAA problem. So it's a very tractable, simple optimization problem. Okay? So let me first explain to you why we have a finite sample guarantee. Actually, this is a consequence of a measure concentration theorem, which has been proved by Fournier and Guillen. So these are two mathematicians, and that's a very, a math paper. So what these two gentlemen proved is that the Wasserstein distance between the unknown true distribution P and the empirical distribution P at n on the n training samples converges to zero somehow exponentially fast as the number of training samples tends to infinity. More formally, you see the statement here. So the probability that the Wasserstein distance between the true distribution and the empirical distribution is larger than epsilon, for some positive epsilon, this probability is small. It's exponentially small, actually, in the number n of training samples, but it is also exponentially small in the tolerance epsilon. So what this means, if we have a Wasserstein ball of radius epsilon around the empirical distribution, then the probability that the true distribution, which we do not know, so the probability that this true distribution is not in the ball is very small, exponentially small in n and epsilon. So what we would like to do is we would like to choose an epsilon such that the true distribution is inside the ball with a fixed probability of at least, say, 1 minus beta, where beta is a small number, like 1% or maybe 5%. Okay, so what can I do to make sure that the true distribution is inside the ball? Well, from the formula here, one thing we can do is we can increase the number of training samples n, and then, well, the probability that the true distribution is not in the ball becomes very small. However, as we said before, well, n is rather something that is given to us. We cannot just increase the number of training samples. These are just historical observations in most applications, and I would have to wait potentially a substantial amount of time to get more samples. However, now we have another possibility. We do not have to increase n. Instead, we can actually increase epsilon. So we can make the ball bigger. And of course, if the ball gets bigger, it should be clear that the likelihood that the true distribution is inside the ball will increase. What we would like to achieve here now is we would like to find a ball that is sufficiently large to contain the true distribution with probability 1 minus beta, but as small as possible still. So we try to find the smallest epsilon such that the probability on the right-hand side here in the measure concentration theorem is smaller or equal to beta. Okay, so if we do that, we get the formula that expresses epsilon as a function of beta, our tolerance, and n the number of training samples. And I will not go through the math, but I mean the formula is shown here in the middle of the slide. So this epsilon and n of beta is the smallest radius for the Wasserstein ball, with the property that the true distribution is inside the ball with probability 1 minus beta if we have n training samples. Okay? And that means that, well, the out-of-sample performance of our data-driven decision x hat is smaller or equal to the optimal value of our distributional robust optimization problem j hat with the same probability 1 minus beta. The reason for that is that j hat is the maximum of the out-of-sample performance of x hat over all distributions in the ball. Since the true distribution is inside the ball with the probability 1 minus beta, well, this maximum is larger or equal to the true out-of-sample performance with the same probability 1 minus beta. So that means our approach really gives us a finite sample guarantee. And this works even if the number of training samples is finite, not like in the SAA method, where we need an unrealistically large number of samples to get a reasonable guarantee. Okay? So let's look at the second property of our wish list, which is the asymptotic guarantee. So we can actually prove the following theorem. We can prove that if the distribution P, the unknown true distribution, has exponentially decaying tails, then if we set the radius of our Wasserstein ball to epsilon n of beta n, where epsilon n is the formula from the previous slide here, right? And at the same time, if we choose the significance level beta n exponentially small with the number of training samples, then we can prove the following. We can prove that the optimal value j hat n of our distribution robust optimization problem converges almost surely to the true optimal value of our stochastic program as the number n of training samples tends to infinity. And we can also prove that any accumulation point of the sequence of optimal solutions of our distribution robust optimization problem as the number of training samples tends to infinity will be an optimal solution for our true stochastic optimization problem. So this is not surprising. It tells us that, well, if you make the ball smaller as the number of training samples increases, then the ball eventually converges to a point which only contains the true distribution, and therefore you would expect that, well, your distribution robust optimization problem converges to the true problem in the sense that it has the same optimal value and the same optimal solutions. Okay. So now let's go to the third property of our wish list, and that's maybe the most interesting one. So we wanted to make sure that our method of data-driven optimization, so our distribution robust optimization problem with the Wasserstein distance, this problem should be easy to solve. We should have computational tractability for it. Otherwise, if it's not easy to solve this problem, then well, there would be no hope for it to be useful in practice. So to show you that this problem is tractable, I need the so-called Kantorowicz-Rubinstein theorem, which gives an alternative dual representation of the Wasserstein distance. So this theorem says that the Wasserstein distance between two distributions Q1 and Q2 can be written as the optimal value of a minimization problem, which minimizes over all distributions Q, which are joint distributions of two random vectors xi1 and xi2, which have marginals Q1 and Q2. Okay, so Q is a joint distribution of xi1 and xi2 with marginal distributions Q1 and Q2, and we just minimize the expected value of the norm distance between xi1 and xi2. So geometrically, the Wasserstein distance between xi1 and xi2 can therefore be interpreted as the minimum cost that you need to pay to move the distribution Q1 to the distribution Q2, when the cost of moving a unit mass from a point xi1 to xi2 is given by the distance, the norm distance between xi1 and xi2. So the Kantorowicz-Rubinstein theorem tells us that the Wasserstein distance has an interpretation as the optimal value of a transportation problem, as we studied sometimes in logistics. But in this case, it's a transportation problem where the transportation plan Q is a distribution. And the supply and demand distributions are just Q1 and Q2. Okay. Now, computing Wasserstein distances turns out to be itself a very difficult problem. It's actually sharply hard, even in simple cases when Q is the uniform distribution on a d-dimensional hypercube. So it's like the simplest distribution, continuous distribution in d-dimensions. And the other distribution Q prime is a two-point distribution. So a discrete distribution with only 2 points. So even in this simple case, computing the Wasserstein distance between Q and Q prime is sharply hard. Actually, let me sketch the proof of this result. So we can reduce the problem of computing the Wasserstein distance between Q and Q prime to computing the volume of a so-called knapsack polytope. Okay? So a knapsack polytope is actually the intersection of a hypercube with a half space. Now, any half space can be expressed as the set of all points that are closer to 0 than to some point W, right? So the knapsack polytope that emerges from intersecting the hypercube with the half space induced by W, this knapsack polytope, we call it P of W. And now it's a well-known fact from theoretical computer science, proved by Dyer and Fries, that, well, computing the volume of the simple knapsack polytope is a sharply hard problem. So it's impossible to do that in polynomial time. unless some complexity theoretic assumption is violated, unless P is NP. Now, let's start with the proof. So let's assume that Q is the uniform distribution on the hypercube, and Q prime is a discrete distribution which places probability alpha to the point 0 and probability 1 minus the alpha to the point W. And now let's try to calculate the Wasserstein distance between these two distributions as the probability alpha of the point 0 changes. So first, if alpha is 1, then, well, all the probability mass from Q needs to be moved to 0. Okay? So actually for any alpha, what I try to do here is now I'd like to visualize the optimal transportation plan for moving probability mass from Q to Q prime. So any transportation plan is visualized by two colors in the hypercube. Okay? So in turquoise, I visualize all those points that should be moved to the point 0. And in magenta, I visualize all those points, or in pink, I visualize all those points that should be moved to the point W under the optimal transportation plan. Okay? And the video shows you now how this optimal transportation plan changes when alpha changes. Okay? And you see actually that, well, the Wasserstein distance between Q and Q prime is exactly minimized when all those points that are closer to 0 are moved to 0, and all those points that are closer to W are moved to W. So in this case, the alpha is exactly equal to the volume of the knapsack polytope, P of W. So now assume, for the sake of argument, for a moment, that it would be easy to compute the Wasserstein distance between Q and Q prime for any alpha. Then it means we could actually evaluate any point on the curve on the right-hand side very efficiently. And by using some simple methods from one-dimensional optimization, we could also efficiently minimize this function with respect to alpha. And that means we could efficiently compute the volume of the knapsack polytope P of W. However, this would contradict the hardness result by Dyer and Fries, which states that, well, computing this volume of the knapsack polytope is indeed a sharply hard problem. So from this, we conclude that computing the Wasserstein distance between a continuous and a discrete distribution, even if the discrete distribution has only 2 points, is actually sharply hard. Okay? Now, actually, even though it is difficult to compute this Wasserstein distance, I will show to you now that our distributional robust optimization problem is actually tractable. It's computationally tractable. And this is very surprising in view of the hardness result we've just seen. So I would like to explain this surprising tractability result to you. But to that end, I need some additional assumptions. So let me now assume that the loss function, let me suppress the decision X. So let's look at the loss function that only depends on the random vector Xi, and I do this just to avoid clutter so that the formulas look easier. Now, let's assume that the loss function is essentially, the negative loss function is convex. So that means the loss function is actually concave, right? So it is downward curve. As a function of Xi, it's a proper convex, the minus L is a proper convex lower semi-continuous function, and that means L is a proper concave upper semi-continuous function. Let's also assume that the set capital Xi, which is the support set of the unknown distribution, is a convex enclosed set. Okay, so under these assumptions, I would like to show to you that evaluating the worst case expected loss over our Wasserstein ambiguity set is a simple problem. Okay, so here I just copy this problem again. As I said, I dropped the X in order to avoid clutter. Now, first of all, I express the expectation as an integral over Q. And okay, so I want my distribution Q to be an element of the Wasserstein ball of radius epsilon around the empirical distribution. And here I use the Kantorowicz-Rubinstein theorem. Of course, if this Wasserstein distance is smaller or equal to epsilon, it means that there exists a joint distribution capital pi of Xi and Xi prime with marginals, so under which Xi has marginal Q and Xi prime has marginal P hat N, such that, well, the transportation cost from Q to P hat n, given by pi is smaller or equal to epsilon. Okay? So this is just the Kantorowicz-Rubinstein theorem. And at the bottom, you see a visualization of this. You see in red the distribution Q, which is some distribution in the Wasserstein ball. The different spikes at the bottom right in blue, green, yellow, and orange, these represent the empirical distribution, so the uniform distribution. In this visualization, we have 4 different training samples. They all have the same distribution. And then you see the joint distribution of Q and P at n, visualized by these vertical geometric shapes which stand in the plane a bit like shark's fins. Of course, this joint distribution needs to have the correct marginals. So if you project it into xi, then you need to get Q, and if you project it into the xi prime dimension, you need to get the empirical distribution. So clearly, this pi, this transportation plan, can be decomposed into 4 different pieces. Actually, it is from the law of total probability, it's clear that this joint distribution can be written as an average of the conditional distributions of xi, given that xi prime is equal to one of the 4 training samples. So we can completely express this joint distribution capital pi in terms of the conditional distributions Q1, Q2, Q3, and so on, Q4, right? And our objective function then becomes equal to the average over the n conditional distributions, and then we take the expected loss under each of these conditional distributions. And the Wasserstein constraint also simplifies to an average of n integrals, where in the ith integral we just evaluate the expected value of the norm distance between xi and the ith training sample xi at I under the ith conditional distribution. So this is just an exact reformulation. And what we've achieved now is we've actually reformulated our optimization problem as a so-called generalized moment problem. It's a problem that has finitely many constraints. Well, there's only one constraint here, and there are actually n implicit constraints, because the QIs, they need to be probability distributions, right? So they need to be normalized and non-negative. But there are infinitely many decisions, because the QIs, these are probability distributions on the set capital Xi, which could be the whole space, or it could be a polyhedron or an ellipsoid. So actually, however, this moment problem is actually a linear program, because the integrals are linear in the probability distributions. So the objective function is just a linear function of the QIs, and the constraints are linear function of the QIs. And actually, there is a duality theory for such semi-infinite linear programs, and we can find the dual. I'm not showing you the details, but the dual is an optimization problem that has finitely many constraints, finitely many decision variables, which are the dual variables lambda and Si. So lambda is the dual variable of the Wasserstein constraint, and Si is the dual variable of the constraints that require these the ith distribution Qi to be normalized. Now, this dual problem has actually infinitely many constraints, because for every realization Xi in the uncertainty set or in the support set capital Xi, we have here a convex constraint, which involves the loss function and the norm function, the norm distance between Xi and Xi hat I. So this is actually a robust optimization problem, okay, where the decision variables are the dual variables lambda and Si, where the uncertainty is the Xi, and where the robust constraints, they need to hold for all possible realizations of the uncertainty. Okay, so that's just an application of the semi-infinite duality theory, which is well known in optimization. Now we can further simplify this. We can actually reduce the robust constraint that holds for all Xi in Xi to a robust constraint that holds for all Xi in the whole space Rm by subtracting on the left-hand side of the constraint the indicator function of the set Xi. So this indicator function evaluates to 0 if the vector Xi is inside capital Xi, and which is equal to plus infinity if the vector Xi is outside of capital Xi. Okay? And now we can actually so this constraint needs to hold for all xi and xi. So the left-hand side of the constraint is a function of xi. For every xi, this needs to be smaller or equal to Si. This is equivalent to saying that supremum of the left-hand side over all xi in Rm must be smaller or equal to Si. So I have reformulated my robust constraint by a constraint that involves an embedded maximization problem. Okay, and now we can again use a trick from the literature. Actually, this maximization problem can be dualized, and it becomes then a minimization problem. And in doing so, we pick up some additional dual variables, which are denoted by Zi and Vi here. And so I skipped the details, but that's a well-known technique from a recent paper by Ronnie Bental, Dick Hertog, and Jean-Philippe Vial. So what happens here is now that eventually we can reformulate our constraint in terms of, well, the convex conjugate of the negative loss function L, so that's this minus L star, the dual norm of the vector Zi, which is a dual variable we picked up here in this dualization, and the support function sigma xi of our support set capital Xi. So all of these, the dual norm, the convex conjugate of minus L, and the support function of Xi, these are actually convex functions, and therefore the optimization problem we found here is actually a simple convex optimization problem. Okay? So we reformulated our complicated problem over all distributions in the Wasserstein ball as a simple convex optimization problem. It's a finite convex optimization problem. The problem size grows only polynomially in the input data. So you see the number of constraints here is if the order of the number of samples and the dimension of the uncertainty. And the number of decision variables is of the same order of magnitude, right? And that means that, well, this problem is really in the same complexity class as the sample average approximation problem, where, well, the number of components in the objective function is also of the size n, right? And actually, so this is a minimization problem, which is very good news. You remember, we wanted to solve a distribution robust optimization problem, which was a min-max problem. Now, we fixed the x and focused on the inner maximization problem, and we reformulated it as a simple minimization problem. So our min-max problem now became actually a min-min problem, and the two mins the minima can be combined to formulate a single minimization problem that you can actually solve with a standard convex optimization solver in many cases. So that's very good news. So, however, of course, this problem, even though it's in the same complexity class as the sample average approximation problem, it's still a more difficult problem. And I would like to show to you that there is actually value in solving this more difficult problem. So for this purpose, let's look again at our portfolio optimization problem. You remember that when we solved this with 30 training samples using the sample average approximation methods, then we had a huge discrepancy between in-sample and out-sample performance. So we had a pessimistic bias, and which led to very disappointing results if we actually implemented our SAA decision in practice. Now let's solve the same problem with a Wasserstein distribution robust optimization approach, and let's calculate again the in-sample performance in green and the out-of-sample performance in red. And you can see there is still a bias. So if you have only 30 samples, a certain bias remains. However, the two distributions are much more closer to each other. So actually the out-of-sample disappointment is much smaller. And in particular, the out-of-sample performance is always much closer to true minimum than under the SSA method. So it seems that this method really significantly improves the quality of our decision. Okay? So now let's go back quickly to our convex optimization problem here, which is a minimization problem. Actually, is there a question? Well, the thing is, if you have, so the outer minimum is over x, and the loss function here in this problem in general depends on x, right? So here when it made this derivation, I suppressed the x, but now we can introduce it again. So the L depends on x. And now I just combine the minimum over x with the minimum over lambda, Si, Vi, and Zi. And we can actually just combine these two minima to a single minimum over x, lambda, Si, Vi, and Zi. And that is always allowed because that's a general result in optimization. So if you have several variables over which you optimize, it doesn't matter in which order you optimize, and you can also optimize jointly. So you will always get the same result. So if you have two minima, you can swap them or interchange them. It won't change the result. If you have a minimum and a maximum, there you know that that's not always possible to switch them, right? Only in special situations, as they are studied in duality theory, you can do that. But in general, you pick up an error. But if you have two minima, you can interchange them. So that's the reason why we can combine here. Okay. Okay. So now our minimization problem, I can actually dualize again to gain another convex maximization problem. Any convex minimization problem can be dualized to get a convex maximization problem. And that, under mild conditions, there will be strong duality. So this will have the same optimal value as the minimization problem. And that will therefore also be equal to the worst case expectation that we wanted to calculate. Now, the dual problem is shown here on this slide. And this is a very nice interpretation. Actually, it can be interpreted as a version of our worst case expectation problem, which evaluates the worst case expectation only over discrete distributions. And each of these discrete distributions places a probability of 1 over n to a perturbed training sample. So the perturbed training sample is at the point xi I hat minus qi. So qi is a displacement. So I should move the ith training sample by qi. I need to make sure that I displace the sample inside the set capital Xi. And I should make sure that the average of all displacements is smaller or equal to epsilon. That's just a Wasserstein constraint. So what this actually tells us is that actually we could have restricted attention to only discrete distributions or perturbed empirical distributions in the Wasserstein ball without changing the optimal value. And that is surprising. That means, well, the worst case must be attained by a discrete distribution. In fact, I can solve the maximization problem on this slide. Let's say the optimal solution is qi star up to qn star. Then I can construct a distribution capital Q star as, well, the empirical distribution on the perturbed samples, xi hat I minus qi star. And, well, because of this result, well, this shows me that this is actually the distribution that attains the worst case in our maximization problem. So I can explicitly construct what is the worst case distribution for me. Okay, so here's an example. Let's assume that I want to find the worst case expected value of a quadratic loss function. So the level sets of this loss function are visualized by the concentric ellipsoids here. And you should think of so the function is maximal in the middle of the plane, right? So it's a concave function, right? In the middle, it's maximal, and it goes down as we move away from the minimum. Now let's assume the training samples are the red dots here. Now, of course, these are not randomly chosen, but they're nicely arranged in a grid. And, well, that's just for better visualization. So normally these would be random points. Now, if the radius epsilon of the Wasserstein ball is 0, then, of course, well, the Wasserstein ball is just a point. It only contains the empirical distribution. So these are the dots that we see here. These are the empirical samples. Now I'll show you a video when epsilon increases, then, well, nature will try to move the samples so as to make the expected value of our loss function as large as possible and to hurt us as much as possible. And, okay, so the video will see that nature first moves the points that are far away from the center because there the function is steeper. And at a certain point, well, if the radius is big enough, then nature can move all the probability mass to the center of the plane, which is the point where we have the global maximum of our loss function. And there, well, our worst case expectation just becomes equal to the worst case value of the loss function. In this case, we're no longer distributionally robust, but we're actually robust. Okay? And we can also generalize the results I showed you to other loss functions. So far assumed that the loss function is concave, I can actually extend all results to loss functions that are pointwise maxima of finitely many concave loss functions. And well, then I can show you a few special cases of where this is applicable. Assume, for example, that the support set capital Xi is a polyhedron described by linear inequalities, and assume that the loss function is a pointwise maximum of affine functions or a pointwise minimum of affine functions. Well, if we have a pointwise maximum of affine functions, then, well, our generalized tractability result applies because every affine function is concave. On the other hand, if you have a minimum of affine functions, then you can see from the visualization that, well, if you have a minimum of affine functions, it's actually a concave function. So our original tractability result applies. So in all cases, we can find a simple reformulation of our worst case expectation problem as the optimization problems that are shown in this table. And I should point out that these are very simple problems. All the constraints are linear, except the one that involves the dual norm of the original norm. And even that one can be reformulated as in terms of linear constraints if we use as a transportation cost the one norm or the infinity norm, which are polyhedral norms. So that means in these cases, these are just simple linear programs that you can solve with Cplex or Gurobi, which is quite surprising, I think. So these are, in this case, simple convex linear programs. If you use the Euclidean norm as a transportation cost, then the dual norm is also the Euclidean norm. And in this case, this will be two second-order Cohn programs. Okay, so in the interest of time, I'll go a bit fast here. So you can also use this for two-stage stochastic programming when the loss function is itself the optimal value of a minimization problem, say a linear program. So if the uncertain parameters are the objective function, then this loss function is a concave and piecewise affine function. And if the uncertain parameters are in the constraints, then L of Xi is actually a convex piecewise affine function. And that means in both cases, we can find an exact tractable reformulation of the worst case expectation problem. So that means these techniques can be not only used for single stage stochastic programming, but also for two-stage stochastic programming. Oops, we can also even use this technique for finding worst case probabilities of some sets. So let's assume that set A is a polyhedron, and you want to find the worst case, so the maximum probability that Xi, the random vector Xi, is in the set A. Now, this can be expressed as, well, the probability can be expressed as an expectation of the indicator function of the set A, and the indicator function here just evaluates to 1 if a particular Xi is inside the set A, into 0 otherwise. And now this indicator function itself can be seen as a pointwise maximum of two concave functions. The first one is just the function that is constant at 0, visualized in green. And the other one is just a concave function which is equal to 1 inside the set A and equal to minus infinity outside of the set A. So you see the maximum of these two, the red and the green function, that is actually equal to the indicator function on the left-hand side. And therefore, the techniques we developed can be applied. As a similar but a bit more complicated construction applies if you want to find the worst case probability that Xi is outside of the set A. So let me give you an example. So the set A here is the diamond, the blue diamond, and let's assume the training sample are again the red dots here nicely aligned in a grid. So on the left-hand side, I would like to calculate the worst case probability of the diamond. So nature tries to move probability mass inside the diamond. If the Wasserstein radius epsilon is 0, then, I mean, the samples that are inside the diamonds, they count, and those that are outside, they do not count. If the radius epsilon increases, then nature will try to move probability mass into the diamond to make its probability bigger. And you can see that it will first move the close samples and then move the samples that are further away. And if the radius is big enough, eventually all the samples will have been moved inside the diamond, in which case the worst case probability is, of course, 1, which is a trivial upper bound on any probability. On the left-hand side, I'd like to do a similar experiment, but in this case, nature tries to move probability mass outside of the blue diamond to maximize the probability of the white space around the blue diamond. So here, actually, because the construction is more complicated, this looks a bit psychedelic, and nature will actually try to split up certain training samples into smaller samples, and eventually, if the radius is big enough, it will also move all the samples out of this blue diamond. So as a last example, I would like to come back to our portfolio optimization problem, and I would like to analyze the optimal solution of this problem when we solve it with the Wasserstein distribution robust approach. And I would like to increase now the radius of the Wasserstein ball. Now, the picture on the right-hand side shows you the weights of the 10 different assets in the optimal solution as a function of the radius epsilon. What you can see is that if epsilon increases and becomes very large, then eventually all the weights will be equal. And that's actually something we can prove. So we can prove that if the radius epsilon goes to infinity, then the so-called uniform portfolio, the 1/n portfolio that assigns equal weight to each asset, is optimal. And that's actually interesting because it has empirically been observed by De Miguel, Garlapi, and Upal in 2009 that actually it is very hard to beat the uniform or the 1/n portfolio out of sample with any optimization-based methods. So if you just naively use, say, a Markowitz approach to portfolio optimization, then out of sample, if you really simulate realistically what happens, you will most often do worse than the 1/n portfolio, which is just a very naive portfolio strategy. Just divide your capital into n equal parts and assign all of them to the 10 different assets. Now, what our result shows is that actually this 1/n portfolio is optimal if there is high model risk. So if there is a lot of uncertainty about the true distribution of the assets, then the best thing you could do or should do would be to implement this 1/n portfolio. Okay, so I think in the interest of time, let me stop here. I would also have some slides that analyze the optimal solution as the sample size increases, and we would see that we do much better than the SAE approach. So the distribution robust approach converges much faster. And I would also have some applications of this method to machine learning, where we show that you can actually use distribution robust model to, say, solve a logistic regression model. And we can prove that in certain cases, classical logistic regression with a regularization term can be seen as a special case of a distribution robust logistic regression model. There's a theorem for that. So that gives us actually a theoretically sound explanation for why regularization may work well in practice. That's something that is done always in statistics, right? So we give a probabilistic interpretation of regularization in terms of Wasserstein distribution robust optimization. But because of lack of time, I should stop here, and I'll just end with a slide which gives you some references of the papers that were covered in this talk. So I'd like to thank you very much for your attention, and